All right, good morning, everyone. Welcome to today's class. So another week passed, so let's have a review about what we have learned last class. In last class, we introduced convolutional neural network. So basically, we learned two new types of layers, the convolution layer and pooling layer. But for CNN, usually we also need the fully connected layer because we also need to do the classification at the output layer. So that's all the layers we have learned in last class. And we also checked like the overall training process of CNN. But we are not finished yet. Because even though we build up all the layers for CNN and we do such overall training, there are some easily happening problems, overfitting and underfitting. So actually, we also learned this in MLP, right? In MLP, we already introduced what is overfitting and underfitting. And we have said about that, usually for neural network, underfitting does not occur because if you find that your model is not so good, then basically you just increase your parameters, the number of parameters. Then definitely you can overcome the underfitting problem. The more common problem in neural network, including MLP and CNN, is overfitting. Overfitting means that now the model was trained too much on the training data, even including some noise, possibly including some outliers. In this case, the model just overfitted and will not perform well on some unseen data. Like here is some examples on the, actually this is the regression task, as you can see. This is the polynomial fit. So if our data just looks like this, then if we just use some linear regression to do this regression task, then it's definitely underfitting. So as you can see, not fit at all. Actually, we can also check the training error and generalization error. Training error is an error measured on the training data. Generalization error is an error measured on some unseen new data. So in this case, the training error is 0.4 and generalization error is 0.42. If we set the polynomial fit degree as 4, in this figure shows that actually this is a good fit, can fit the training data. In this case, the training error and generalization error are both very small, 0.14 and 0.17. If we further increase the polynomial fit degree, like in the rightmost figure, if we set the degree to be 20, we will learn some regression like this. So as you can see, it looks very well, but actually it matches the training data very well. In this case, the training error is only 0.07, almost 0, but the generalization error is 2000. So basically it cannot fit any more of the unseen data. So this is the overfitting. So in order to avoid such overfitting problem, actually we have to find some ways to decrease the number of parameters or to make our model somehow smaller. Whenever you observe that, okay, there is some overfitting. And here is one technique that you can use to prevent overfitting in neural network. Actually, almost in all types of neural network, you can add such layer, dropout layer to avoid overfitting. So the large neural network they trained on some relatively small data sets can overfit the training data. Sometimes it's very severe overfitting. This has the effect of the model learning some statistic noise in the training data, which just results in the poor performance when the model is evaluated on new data. For example, a test data set. So like if you find that during training, the loss is just decreasing, but however, the accuracy or the loss in the validation data just does not seem very well, then that's overfitting. And the generalization error just increases due to the overfitting. And in this case, we can simply apply the dropout layer to prevent from overfitting. So dropout, even though we call it dropout layer, actually formally it's some regularization method. So during the training, we randomly drop out some number of layer outputs. just randomly drop out, randomly ignore. And dropout has the effect of forcing the nodes within a layer to probabilistically take on more or less responsibility for the inputs, because some of them will just be ignored. And because the outputs of a layer under the dropout are randomly subsampled, it has the effect of reducing the capacity, or you can regard it as some thinning the network during the training. As such, usually maybe we will need some wider network. So that means more nodes, because we know that some of the nodes will just be dropped out. Then how to drop out? Dropout actually is implemented per layer in a neural network. So that means you have to first already have a layer. Then you can implement such dropout layer after your layer. For example, fully connected layers. After you have a fully connected layers, you can add a dropout layer, and convolutional layer can also be implemented with a dropout layer. Right after convolutional layer, you can have a dropout layer, and dropout may be implemented on any or even all hidden layers in the network. And possibly, dropout can also be applied in the input layer, but usually we don't. Even though we can, but usually we don't implement in the input layer because the input are the raw inputs. Right? Usually we just assume that the inputs, they are important. Definitely, dropout layer cannot be used on the output layer. It doesn't make any sense if you have a dropout layer after the output layer. Right? Because output layer is a classification results. It doesn't make any sense if you just randomly ignore some of the classes. So in this case, a parameter is introduced in dropout layer. But even though we see that it's a parameter, but this parameter is not learned by the network. This parameter is set up by ourselves. This parameter should specify the probability at which the outputs of the layer are dropped out. Or inversely, the probability at which outputs of the layer are retained. For example, you can set it at 0.5. This is a common probability. That means you want to have 50% probability that retain the output of each node in a hidden layer. So for example, possibly this would be the results of one dropout. So previously we have this fully connected layer, right? Like each node is connected with each node in the next layer. After you apply some dropout, then it will just randomly select whether it should ignore some nodes with the 50% probability if you set it to be 0.5. For example, it may just, in some one step, it may just think that, okay, after some probability random sampling, these two nodes should be ignored, these three nodes should be ignored, these two nodes should be ignored. After they are ignored, note that they are just totally randomly decided. After these nodes are ignored, as you can see, the number of edges reduced significantly. That's how the dropout just tries to reduce the model capacity. It tries to reduce the model capacity because it wants to avoid the overfitting. So after drop out some of the nodes, the number of edges actually just becomes smaller, and then it tries to reduce the overfitting through such mechanism. So this is the dropout. So any question regarding dropout layer? Great. During the PA2 and Lab 8, I think you will have some chances to practice with the dropout layer. All right. Then next we will revisit a task we have done before, handwritten digits recognition. And now we are using CNN to perform this task. So recall that handwritten digit recognition, the data looks like this. So we will have some handwritten digits as our input data. They are all image data, and we want to predict these handwritten digits into the classes 0 to 9. So now we will build a CNN model to do this task. The data set still, we just use the MINIS data set. It contains two sets of samples, 60,000 training data, 10,000 testing data. all the data, there are some 28 by 28 images. And in this case, we just simply use the grayscale images because the color doesn't matter. So all of these data, actually, they are grayscale images. And then now, the procedures of building a CNN would be like this. First, we import required libraries and define some global variables. This is always the first step. You must have some libraries and before you can manipulate on the data and the model. And then load and prepare the data. And note that in this case, we don't do the data exploration because we have done this before. If you already forget the data exploration step, you can refer to the lecture on MLP for the data exploration. So here we just omit this step. After load and prepare the data, we build the model. And then we compile the model, train the model, evaluate the model accuracy, save the model, use the model. So all the following steps are just the same with MLP. It's just some typical pipeline for the neural network. Okay, import the libraries. Most libraries actually we have seen in the MLP lecture. Some new libraries and some new modules here. We now import the comp2d and maxpooling2d from the keras.layers. This will be the two new layers we need to use, the convolutional layer and maxpooling layer. They are both in 2D cases because the images, they are just 2D data. All right, and here we also imported dropout, as you can see. This will be the new types of layer we will use. Another function we will import is called the toCategory. Later on, we will see that this function is used to do the one-hot encoding. Okay, I think all the following libraries actually we have already seen them on the MLP. Some global variables, we set the batch size to be 128. Batch size is the number of samples per gradient update. Previously, when we introduced the gradient descent in the MLP, actually we have done some training that each step we just give one data sample to the neural network to update, right? One data sample, we do one forward propagation, one backward propagation. That's one step. But actually, we can try to improve the efficiency, so speed up the whole training process by set the batch size. The batch size is that now, per gradient update or each step, actually we will give 128 input data to the neural network to let it update the parameters. In this case, actually the training will be much faster. And the number of classes is 10, epochs is 1, so we still just only train our model for one epoch. And the image dimensions here we specify here. This will be the first step. And then second step, we load and prepare the data. Loading part is the same with MLP. So simply we use this min_list.load data, and now we can get this X train, Y train, X test, Y test. Next, we will prepare the data a little bit so that it can fit the CNN's input. So X train, we know that X train is actually a NumPy array with this shape, 60,000, 28, 28. X test has this shape, 10,000, 28, 28. First, we reshape X train and X test. So we reshape X train to be in this shape, 60,000, 28, 28, 1, and X test is the same. Basically, just we append a new dimension at the end so that now the data becomes 4D. We have to do this. We have to do this because for the convolutional layer, the input must be 4D. If you want to use the convolutional 2D layer, what does it mean for this 4D? If we regard it as some input for the convolutional layer. For convolutional layer, the first dimension is always the number of data it accepts. So this one, we must leave this position for the number of data. And then the second and the third dimension, 28, 28, will be the spatial dimension. Spatial dimension means that basically that's the size of the image. The last dimension is the depth, the number of channels. Because the convolutional 2D layer actually will accept the depth information. So if it's, for example, if it's RGB image, then this depth is 3. right? Even though it's grayscale imagery, we have to let this dimension representing the depths. So we have to put a 1 here. Otherwise, the comp 2D layer will not accept such input. So we have to give this depth information. That's why we have to do such reshape if we want it to be some input for CNN. All right, this is how we process our data. We still need to do some steps to process our labels. So here the labels, we do the one-hot encoding. Actually, we introduced a little bit about the one-hot encoding when we introduced the cross-entropy loss. Right? If you still remember the cross-entropy loss, actually the labels Y is represented using the one-hot encoding. So here we do this one-hot encoding by simply apply this function to categorical. To categorical, we need to first give the label array Y train, and then we need to give the number of classes. After that, it will automatically do the one-hot encoding and give something like this. So this is an example of one-hot encoding. So basically, this function to categorical converts some class vector. Class vector means that they are integers from 0 to the number of classes. Convert such class vector to some binary class matrix. Binary class matrix means that all of their values are true or false, or 0 and 1. Usually we do this because we use categorical cross-entropy loss. For this entropy loss, all the labels are just represented using the one-hot encoding. So for example, if we have Y train like this, so basically now, as you can see, we have 8 data samples. Each of the data samples label are stored in Y train, and the total number of classes is 6. So that's from 0 to 5. We have 6 class labels. And after we apply this to categorical Y train, number of classes equal to 6. The output will just be like this. The output will be some 2D binary array. The number of rows is the number of data samples. Previously, we have 8 data samples here, right? In total, we have 8 entries. So in this output, we should have 8 rows. Each row is just 1 data sample. And we will have 6 columns because in total we have 6 classes. So the number of columns will be the number of classes we have. So 6 columns. And now we will just put 1 at the corresponding index representing the label. The first data sample has a label 1. So that means the first row should have 1 value in the column 1, so here, and all others just be 0. And then the second data sample, the class label is 0, so that means it should have the value 1 at the column 0, so that's why we have 1 here, and all others are just 0, so on and so forth. So as you can see, each row will only have 1 value 1, and all other entries are just remain 0. So we use the column index to represent the class label. So this is the one-hot encoding. Then when to use the one-hot encoding? The one-hot encoding will be used in a situation where the data has no relation to each other. Because if we don't do one-hot encoding, then all the class labels will be arranged like from 0 to the number of classes, like previously from 0 to 5. But in the machine learning algorithm, actually, we know the order of integers, they are treated as some significant characteristic, right? 0 and 5, actually, they have some values, and there are some orders to arrange these class labels. So in other words, usually a large number will be interpreted as better or more significant than a smaller number. This is useful in some scenarios. Certain input data, actually, they can be regarded as such thing, can be interpreted as such thing. But if the labels, if we are considering the labels, then basically the labels, they do not have so much difference with each other. Like the input data, they lack a ranking for such categorical values. In this case, actually this will just cause problem with the predictions and performance. Because possibly we just randomly select the integer numbers for some class labels. For example, if we are doing the classification, animal classification, we have 3 classes, cat, dog, and none of them, the 3 classes. Then possibly you have one way to represent them using integers, like you use 0 represent cat, 1 represent dog, and 2 represent none of them. This is one way. But of course, you can rearrange that. You can use 0 to represent none of them. You can use 1 to represent cat. You can use 2 to represent dog. So actually, you just have different ways to use the integer to represent class labels. And it doesn't make any sense if you see that actually one class label is more important than the other, simply because you assign a larger index to it. In this way, we need to do the one-hot encoding. We don't want to have some ranking of the class labels. Instead, we just represent all of them using the binary array like we have done here. In this case, actually, we try to eliminate the ranking of the class labels integers. Then the benefits of one-hot encoding that now the training data is more usable and expressive as a result of the one-hot encoding, and it can be rescaled easily. Rescaled means that now if you have more training data, basically you just need to implement more rows in such one-hot encoding results. And question, why is one-hot encoding applied to labels? I think the above explanation actually already answered this question. Because actually the labels, it doesn't have any relation to treat them as different values, from 0 to some number of classes. So basically we just do one-hot encoding. And of course in practical implementation, we need to do the one-hot encoding to apply the cross-entropy loss. All right, so any question regarding the one-hot encoding? Great, so for one-hot encoding, if you want to do that, just use these 2 categorical functions. Even though it's not hard to implement by yourself from scratch, but still, if you use this function, it will be very convenient. And recall that this function is imported from the HKUST utilities. All right, then next step, we build our CNN model. Build the CNN, of course, we can't from scratch to do it. We have to use some library. So here again, we consider the HKUST. Here is how we design our models. In total, we will have 8 layers, except from the input layer. So right after the input layer, we have our layer 1. Layer 1 is a convolutional layer. Here we use 32 3x3 kernels, and we use the ReLU activation. The input size for the layer 1, that is 28 by 28 by 1. That's the image size and its depth. After the first convolutional layer, we have our second convolutional layer. Now we use 64 kernels. So recall that when we're introducing convolutional layer, we said that the convolutional layer always extend the depth of the output volume. Extend the depth means that the number of kernels should be more and more. So here we use 64, and the size is 3x3. Activation is still ReLU. Okay, after these 2 convolutional layers, we use a dropout layer with a rate 0.25. So it means that it randomly sets the input unit to 0 with the probability 0.25 at each step during the training time, so which will help prevent the overfitting. For all the inputs, if they are not set to 0, they will be scaled up by this 1 over 1 minus 3, so that the sum over all inputs is unchanged. Because actually the sum of all the inputs have some play some important roles during the neural network training. So actually the HKUST will automatically do this rescaling. After 2 convolutional layer, 1 max-reading layer and dropout layer, we will connect it with a flattened layer. Because actually our image data are quite small, right? Only 28 by 28. Each pixel is just a feature. So that means the image data only has like 784 features each image data. So actually it's not a big data. In this case, 2 convolutional layer will be enough. So next we will directly connect it with the fully connected layer. So we believe that now the feature extraction is already enough. Before we connect it with a fully connected layer, don't forget to do the flattening. After the convolutional layer and the pooling layer, the imagery, there are still some 2D imagery, and also they have the depths. In that case, we have to first do the flattening. So flatten all these 2D images into 1D, and then we can connect it with the dense layer. So here we use 128 neurons and ReLU activation. After dense layer, we connect it with another dropout layer with the rate 0.5 to avoid the overfitting. At the end, our output layer is the dense layer with 10 neurons and the softmax activation. Softmax is used to do the multi-class classification. So now each output will just be the probability of the corresponding class. This is how we design our model. After we design the model, we need to implement it. Again, it's just like building up the blocks using the HKUST modules. So first, we need to create a sequential object. In HKUST, sequential already means the neural network. So we first just create such empty sequential model. After that, we need to add our first layer. First layer is a convolutional layer. The convolutional layer is called comp2d in HKUST. Basically, just model.add comp2d, but we need to specify some of the arguments here. The first, filters. Filters means the number of kernels you want to apply here. So the filters, we just use 32. We want to use 32 kernels. And each kernel with the size 3 by 3. So we also need to specify what is the kernel size, 3, 3. Note that filters and the kernel size must be decided by you. This is not something that a neural network can learn. You need to specify this. You need to tell the neural network how many filters you want to add and what is the kernel size. And know that you don't need to specify the kernel depth. You only need to give the kernel size. That would be enough. Because we know the convolutional layer already has the rule that the depth of the kernel must be the same with the depth of the input. So basically, this comp2d layer will know what is the depth of the input, and then it will decide what is the depth of the kernel. So you don't need to tell the comp2d like what is the depth of the kernel. It just knows that. Activation, of course, you need to give this. We use ReLU activation, and the input shape. This is a convention that we always need to give this argument input shape of the first layer in a neural network. Actually, if you look back at the MLP, when we implement that MLP, we also give this input shape, these arguments for the first layer we have used. In MLP, the first layer we have used is the flatten layer because we first flatten 2D image into 1D. At that time, we also give this input shape. The input shape, we only need to give it for the input layer. Actually, for all the remaining layers, as you can see, we never have such arguments. But this must be specified for the first layer in your neural network. The input shape is 28281. Then what about the number of data? Actually, this input shape does not include the number of data because during the training, the number of data may change. It changes with the batch size, right? So actually, the number of data you pass to the neural network, each step may be different depending on the batch size. So basically, it does not count about for the input shape. So the input shape will only be the image size and the depth. That's the 28281. All right, so this is the comp2d. And note that some of the arguments we don't specify, then that means we will just let it be the default value. For example, the padding is valid by default. Valid if you still remember, if the padding is valid, then that means no padding. So by default, the COMP2D does not apply any padding. If you don't want to apply padding, just let it be the default value. Another default value, strides. The strides is 1, 1 by default. If you don't want to change the strides, just you don't need to specify it, let it be the default value. So we don't specify them. That means by default, we just let padding and strides be like this way. All right, this is our first convolutional layer. After that, we connect it with another COMP2D layer here. So the second COMP2D, now we use 64 kernels, so the filters is 64. The kernel size is still 3, 3. We don't need to specify the depth of the kernel, but I believe you know what is the depth of the kernel now, right? It should be 32, because last convolutional layer we use 32 kernels. So that means the output of the last layer has a depth 32. Then in this layer, the kernel should have the depth 32. This can be computed by the carrots. You don't need to specify that. Activation is still ReLU. And so that means by default, in this layer, we still use the padding as valid, no padding, and we use the strides as 1, 1. After that, we have our max pooling layer. The max pooling layer is called max pooling 2D, and we only need to give this pool size, this argument, we use 2, 2. So that means in this operation, it will just separate the imagery into some subregions, non-overlapping subregions with the size 2 by 2 and do this max pooling filter. After that is a dropout layer. Dropout, simply you just use this one, model.add dropout, and this is the dropout rate you want to apply, 0.25. Then we need to do the flattening. Flatten the data, the image data we already have to some single column, this 1D data. So simply use this model.add flatten. Note that flatten you don't need to give any arguments. The flatten itself already specified that you just want to convert this some possibly multi-dimensional arrays into a 1D array. After flatten, dense layer. Dense layer, you must already be familiar with it. So just use this one, model.add dense. Units is 128, activation is ReLU, and then another dropout layer with the rate 0.5. Finally, at the end, output layer. So the output layer is the model.add dense. The units is the number of classes. We know that's just 10. We will have 10 nodes at the output layer. The activation we use is softmax. After that, we build up our model using the carrots. Just from an empty sequential model, add these layers 1 by 1 until the output layer, and then we finish it. So any question regarding building up the model? Great, no question, then we can continue. Usually after you build up the model, next step, you want to check your model, right? You want to check whether you implement your model correctly, whether actually this model is consistent with what you design here. Check the model, we introduce this model.summary, this function, very convenient for you to check your model, so that you can print out all the informations of the layers, and you can even see like how many parameters you have in each layer. This would be the layer we have. First is the COMP2D layer. Output shape is known 26, 26, 32. Just like the MLP, the first dimension always specifies the number of data it receives. So actually, until now, the model hasn't started to be trained. So we only build the model. Actually, we don't train it. So the first one is still known, but it must leave this position, the known, for the number of data it will receive later. The output shape, then this is the output image size, 26, 26. Our input is 28, 28, 1, right? But we don't apply any padding. The padding is valid. That means we will ignore all the border pixels who do not have the 3x3 label, because we apply 3x3 kernels. In that case, the image size just be reduced to 26. And depth is just the number of kernels we applied in this layer. In this layer, we apply 32 kernels, so that should be 32 channels, or the depth is 32. This is the output shape for the first COMP2D layer. The number of parameters is 320. Later on, we will talk about how to calculate the number of parameters in a convolutional layer. Second layer, another COMP2D layer. Now, the image size further decrease because still we don't apply any padding. The image size becomes 24 by 24. Depth is the number of kernels we applied here, which is 64, and the number of parameters increase largely, as you can see. Actually, with the convolutional layer, you add more and more, the number of parameters will just increase somehow very fast. Then the max pooling layer, max pooling 2D. After the max pooling, the output shape, we know actually it only reduced the image size. Previously it's 24 by 24. After we apply 2 by 2 pooling size, the image size will become 12 by 12. It will be reduced by half, but the pooling layer will not change the depth. So the depth is still 64. And pooling layer does not involve any parameters, because basically the pooling operation is separating the image into some subregions and apply some calculation, like apply the max or apply the average, but actually there is no parameter at all. So for pooling layer, number of parameter is 0. And then dropout layer. Note that the dropout layer does not change the output shape. It's just randomly ignore some of the nodes, but it's not deleting these nodes. So the output shape still remain the same, but just some of the nodes, the output just be ignored. And so the shape still be 12, 12, 64. Number of parameters is 0. Basically dropout, we don't involve any new parameters. Flatten layer simply is that we flatten the previous such array 12, 12, 64 into a 1D array. That is 9216, and the number of parameters is 0. The flatten does not give any new parameters. And then the dense layer. Dense layer, after it, the output shape should be 128 because we apply 128 neurons in this dense layer, and the number of parameters. Actually, we introduced how to calculate this one in the MLP, right? So that should be 9216. This is the number of nodes in last layer plus 1. That is 9217 times the number of nodes in this layer, that is 128, and then we can get this number. Then another dropout layer. Dropout layer does not change the output shape, so it's still known 128. Number of parameters is 0. Finally, output layer is another dense layer. The final output should have the shape 10. It basically just outputs 10 probabilities. Number of parameters in this layer is 1290. So the dense layer. And the total parameters, basically it's just we add all the parameters up because all of them are trainable parameters. All of them should be updated during the training. Then the question would be how to calculate the number of parameters in a convolutional layer. The rationale is the same with the dense layer. Rationale is that the number of parameters should always be the number of weights plus the number of biases. When we are saying the parameters in a neural network, actually we only have these two types of parameters, weights and biases. But the weights, now the weights in a convolutional layer is the number of entries in a kernel. Because we know that the kernel is some matrix and it has like many values, and each value actually is a weight parameter. So to get the number of weights is equivalent with now we need to get the number of values in the kernel. For each single kernel, the number of values would be the kernel size times the kernel depth. This is the number of entries inside a kernel, and we also need to multiply it with the number of kernels we have applied. The number of biases, each kernel is associated with one bias parameter. So the number of biases is just the number of kernels. So in total, we can rewrite it to be in this way. The number of parameters in a comp layer should be the kernel size times kernel depth plus 1, then times the number of kernels. Like here, for example, the first layer, the number of parameters should be the kernel size, that is 26 times 26, then times the depth, 32, then plus 1, then times the number of kernels. The depth is 1 here. So here the kernel depth is the depth we applied. So this one, it should be 1, 26 times 26. 3 times 3. This is the output shape. Sorry, just maybe to mark it down here. Get it confused. So it should be, the first layer should be the kernel size 3 times 3, then times the kernel depth. The kernel depth is 1. The kernel depth is always the same with the input depth, so that is 1, and then plus 1. And then times the number of kernels we applied in this layer, which is 32. So that's why in the first COMP2D layer, the number of parameters is 320. So actually, we can also get what is the number of parameters in the second convolution layer just the same way. So the second layer should be something like the kernel size is still 3 times 3, but now the kernel depth is 32. The kernel depth is the depth of the input for this layer. For this layer, COMP2D1, this layer, the depth is 32, and then plus 1, then times the number of kernels we applied, which is 64. So for this layer, we apply 64 kernels. So this is how we get this 18,496 by using this formula. So basically is that we directly apply this formula to get the number of parameters in a convolutional layer. Alright, so any question regarding the model summary and how to calculate the number of parameters in a convolutional layer? Great. And we can also plot the model by using this plot model function. After that, we will get a graph like this. So basically, just try to visualize the whole neural network layer by layer. For each layer, we'll have the input shape and also the output shape to tell you that after each layer, what is the change for the shape, or we know that for the activation map. So for each layer, it will just get these results. Alright, so if no question, then maybe let's take a 5 minutes break. After that, we will continue with the compilation of the model.
some pixels to move. Like this is the stride is first the kernel overlaps with this subtree, and then the next step is just this solution.
I understand that, but why is this
Right, so it's not just integer.
Can I understand what's the key in stride? What are you trying to
Stride is actually in order to decrease the output image size. Because after the stride, output image size will get reduced. In this case, we will get some smaller output imagery, and so it will reduce the memory invocation and also avoid overfitting. Yeah, because after we just get images reduced, then the number of parameters will also get reduced.就是一层往上加，加到6层来就可以。5层其实应该也可以。
Alright, let's come back to the class. Next step, compile the model. So after build the model, it's always like we need to compile the model. Compile the model in MLP, we already know compile the model is that we need to specify 3 things. Optimizer. So that is what is the optimization algorithm you want to use to update the parameters. So here we use the Adam. So recall that we talked about that the Adam, currently Adam is the state-of-the-art optimization algorithm. So usually we first try Adam, and now we just set it as the default learning rate 0.001. The loss, again, we use the categorical cross entropy loss. In MLP, we also introduce what is this loss. This loss is a try to measure the distance between the model distribution and the data distribution. Data distribution is represented by the class labels Y, and the model distribution is represented by the softmax output. That's the probability is predicted by the model. That's the cross entropy loss. So that means now our neural network will only have one goal. The goal is to minimize the categorical cross entropy loss. And how to minimize is using the Adam algorithm. And we can also specify the matrix. Matrix basically is for us, for our own observation and monitoring of our model. So every a few epochs, we can try to output the matrix in order to, for example, to see how well our model performs and also whether our model have the overfitting problem. So we need to like output some metric to see that. The metrics, so here we simply use the accuracy. Of course, you can add more metrics inside this list so that you can monitor more metrics. Next, train the model. Again, we want to store our model and we want to like store all the log. The log is that we can track back some experimental metrics and also the whole training history. So we create such logdir to store our log files by using the current datetime, because we want to add the timestamps of this logdir so that it won't overwrite itself. And then we create this TensorBoard callback using this TensorBoard, set the logdir be the logdir, we store all the files there, and also histogram frequency is 1. In this case, every one epoch, it just outputs the information. Of course, you may think such training process is a little bit noisy. Every one epoch, you will just see all of these metrics, the loss. If you don't want the model, the training to be so noisy, you can also set the histogram frequency to be a larger number. For example, 5, then every 5 epochs you can see the results. But since now we only train our model for one epoch, so we just set the histogram frequency as 1. Next, train the model. Train the model need to use this model.fit, this function. We pass xtrain, ytrain as a training data and training label to the fit function, and we specify the batch size. The batch size, at the beginning, we define the global variable. Batch size is 128. Usually, like for this scale of training data, like now we have 60,000 data in total. For this scale of data, it's okay, just set the batch size to be 128. But if your data is very small, that is, if you only have like a few hundreds data, then the batch size will also be reduced accordingly. If you have like more data, then you can also increase the batch size. So basically, it depends on how many data you have. Then we specify the epochs. We will only train it for one epoch. The global variable, we define epochs to be 1. Then validation data, we directly use the testing data as our validation data. Of course, it's somehow kind of cheating. That means during the training, we will already let the model evaluate on the testing data. But since it's just an example, we just use the test as a validation data. And the callbacks is the TensorBoard callback we just created. After we run this line of code, the model.fit, it starts to do the training. So you will see a training bar, and it like resembles the training process. And after that, it finishes training for one epoch. Then we can evaluate the model accuracy. So directly use this model.evaluate, use this x test, y test as the testing data, and the wobbles is 0. A wobbles is 0 means that's silent, so then there is no progress bar to show you the evaluation this process. But of course, you can also set the wobbles to 1, and that means it will have the progress bar to show you that. After that, we print the loss and accuracy. The validation loss is 0.072298, something like this. Of course, the loss does not mean much things for us. What we want to see is the accuracy. Actually, the loss the loss is meaningful for the neural network model itself, because it tries to minimize the loss, but it does not like have much meaning to us. We only care about accuracy if we want to see how well our model performs. The accuracy is quite high. Only training for one epoch, it can achieve this 0.9776999, this very high accuracy, which means that our model is very good. we design our model very good so that it can achieve such high accuracy even only trained with one epoch. Since our model is very good, let's save the model. Again, we save it to be this HDFS files. That's the Hadoop distributed file system using this .h5 extension. Of course, Keras provides more various types of data you can save. Like I think in Lab 8, actually you need to save it as the Keras model. They are just different extensions with different files, but they are all readable by the Keras. The model name, let it be this digit recognition cn.h5 and save it as the h5 format. After you save the model, you can load your model to reuse it. Let the loaded model be load model name, and then you can load it. Then you can use the loaded model. So here we use some interactive mechanism to let the user specify which data want to test. So let the imaging index be some user's input, get it from user. So it will input like enter an imaging index and gets what the user typed. And then it can show the image in the grayscale. After that, predict such image for user. So be this function loaded model.predict and then give this x-test image index. And don't forget, need to reshape it to be 4D, 128.28.1, because the CNN accepts 4D data. It must have this depth information and get a prediction and can predict the result for the user. And if we want to get the prediction result, we need to apply this argmax, because the prediction itself is a 1D array with 10 probabilities. If we want to get the true classification results, then we need to use this argmax. Select the index with the maximum value. And this will be some example. Like we let user to enter an image index, and users, for example, user type 10, and then it will show user with such image. This is the 10th image in the testing data, and the predicted result is 0. And this is the 20th data, predicted result is none. So actually this is not so easy for neural network because for such an image, actually the neural network may just easily confuse this 9 with 7. They are very similar. But for our CNN, actually it can predict it correctly as 9. And then the 30th data, the predicted result is 3 for such data. Alright, so that's all the steps of the handwritten digit recognition using the CNN. The steps, of course, the framework are the same with the MLP, but the building the model and also compiling the model will be somehow different. Compiling the model, if you look back at the MLP, even though we all use the categorical cross entropy, but in the MLP, actually, we use the sparse version, a sparse categorical cross entropy version. And that's why in the MLP, we don't do the one-hot encoding. If we use the sparse, actually, it will know that it should first do the one-hot encoding. But if we directly use the categorical cross entropy loss, then we need to do the one-hot encoding when we pre-process the data. This is a little bit different. Others are almost the same, only the model design and the model building up are significantly different. Alright, so any questions so far regarding the handwritten digits using the CNN? Great, if no question, then we can talk more about the typical CNN architecture. So that is how to design a CNN model. Typical CNN model for classification tasks, they stack the different types of layers. First, it have a few convolutional layers, usually with a ReLU activation. We said that for hidden layers in CNN, typically we just use the ReLU. After a few convolutional layers, we can connect it with a pooling layer. Then we stack it again with some convolutional layers, and a pooling layer, and so on. As you can see, the CNN basically that you have a sequence of some convolution layer with a pooling layer, then some convolution layer with a pooling layer, and so on until you think that is enough for the feature extraction. The convolution layer and pooling layer used in CNN, they are used to extract the features. So until you think that the feature extraction is already enough, the neural network can extract the useful information. After that, we connect it with the fully connected layers. So we can connect it with one or more fully connected layers. Again, use the ReLU activation. Of course, between this sequence of comp and pooling layer and the fully connected layer, you need to do the flattening. Otherwise, it cannot connect with the fully connected layer. And then the output layer is a final fully connected softmax layer if you want to do the multi-class classification. This is a typical CNN architecture. So generally, the convolution and the pooling layers, they are for feature learning, and the fully connected layers, they are for classification. So doing through the convolution layers, the feature maps are just the outputs of each convolution layer and pooling layer. The feature maps, typically, they will get smaller but deep. So that is, there will be more feature maps per layer. So get smaller, this will be done by several possible techniques. First, if you don't apply padding, then it will get smaller, right? The output definitely gets smaller if you don't do padding. Another possible way to let it get smaller is applying stride. If you apply a larger stride, for example, let stride to be 2, then the output map, feature map, will also get smaller. Another technique is, of course, you can apply pooling layer. By applying pooling layer, it also reduces the size of the maps. And get deeper, this can only be done by applying the kernels, because the depth of the feature map is just the number of kernels you applied in convolutional layer. So if you want it to get deep, then you need to apply more kernels in the convolutional layer. This is how we can get the feature maps smaller and smaller and deeper and deeper. Then the fully connected layers, they form some ordinary feed-forward neural network to which the transformed inputs are fed. So another rule, conventional rule, is that instead of using the convolutional layer with very large kernel size, for example, 9x9 with 81 parameters, not so accurate. Actually, this 81 is only for weight parameters. If we have some 9x9 kernel, then it has 81 weight parameters. So instead of doing this thing with a very large kernel size, it's better, and we always prefer to stack 2 convolutional layers with some smaller kernels. For example, we can have 2 convolutional layers. Each convolutional layer, we have the kernels with size 3x3. In that case, we will have 18 weight parameters for the 2 layers together. This is a conventional way to that. This is because if we use a very large kernel size, 9x9, and basically we know that image convolution is just some local operation, right? Back to the image operation is some local-based operation. If we use a very large kernel size, it will be somehow more like some global operation because it considers a very large neighborhood size when gets the output for a single pixel. In this case, it may not be so accurate because it just includes and considers some not so relevant neighbor. Actually, 9x9 is already very large, so that means the pixel, we want to get the output, we also consider like some distance with this pixel with 9. It's already far away, right? After 9 pixels, actually, the things will change a lot. So instead of doing this, instead of doing like using a very large kernel size, we prefer use some smaller kernel size, like 3x3, so that we can consider some more accurate local information, some more detailed neighborhood information to get the outputs. So this is some conventional rule of the typical CNN architecture. And at the end, we have some practice problem. This one is to revisit how to do the image convolution, you can try to practice in this problem to see like whether you still remember how to do image convolution. And another practice problem is like assess whether you already well understand the convolutional neural network by answering these questions. So you can compare your answers with the appended answers here. All right, so that's all about CNN. Any questions so far? Yes, please.
On that side, how did we get the number 18?
Oh, 18. Oh, yes. It's 18 because if we consider one single kernel with the size 3 by 3, then the number of weight parameters is 9. And if we use like 2 convolutional layers, then that's 18. Okay. Of course, that's just roughly because possibly we use like multiple kernels. Yes. Okay, thank you for your question. Any other questions regarding CNN? Great. If no question, then yeah, we can do a simple quiz to assess whether you already well understand the important concepts in CNN. So you can join this quiz by scanning the QR code. All right, so has everybody joined yet? Great, then we can start our question 1. Okay, the majority can get it correct. The convolutional layer, number of weights. Number of weights means that the number of entries in the kernels. It depends on the depth of the input volume. Because the depth of the kernel will just exactly be the same with the depth of the input volume. So the number of weights depend on that. And the number of biases is just equal to the number of kernels. Each kernel is associated with 1 bias parameter. So this statement is true. Okay, let's check the leaderboard. Okay. The midterm still below me. Okay. Move on. Okay, move on to the final. Don't always look back at the midterm. Like the final about mean. This is a good name. Okay, like looking forward. Okay, good. Okay, next question. Okay, this is true. If you observe a large gap between training accuracy and the test accuracy, usually that means the overfitting occurs. And we know dropout is a commonly technique to reduce this gap because it can avoid the overfitting. So that's why this statement is true. Drop out to try to avoid the overfitting. Let's check the current leaderboard. Okay, good. The final about me is number 1, and midterm still below me is also very good for this one. Okay, next. All right, this is true. First thing leverages the image convolution. We know image convolution is local-based operation. And the neurons, yes, now we know that the neurons is the kernels now, right? Basically, the kernels are the neurons in some convolutional layer. So the neurons respond to a subset of the input space. So each operation or each computation in the image convolution is that the kernel only responds to a subset of the input space, only responds to a subregion depending on the kernel size to get some output. So that's why this is true. Local-based operation, true, that's image convolution, and neuron response to subset of the input space, true. Basically, that's how we do the image convolution. So let's check the leaderboard. All right, congratulations to midterm still below me. And yeah, I believe you will get like above me in the final, like you have done so good in this quiz. We still have some multi-choice questions because because the quiz module does not allow multi-choice, so we put it at here. So you can try to answer this question. Know that it's multi-choice, so possibly there will be more than one correct choice. Okay, let's show the correct answer. Actually, the majority already get it correct. Correct answer would be the convolutional layer and pooling layer. An input layer itself is just some input features, so it's not used to detect the patterns or features. Convolutional layer and pooling layer, they are used to do the feature extraction and the pattern recognition. Flattened layer basically only has some functional usage to do the flattening, converting multi-dimension to 1D. And fully connected layer and output layer, they are used to do the classification. So only convolution layer and pooling layer in CNN are used to do the feature extraction. So the correct answer would be the second and the third one. And we still have our final question. Again, it's some multi-choice, so possibly there will be more than one correct answers. You may need some time to read these choices about the pooling layers. All right, let's directly check the correct answer. Correct answer would be the second, third, and the last. So let's try to analyze them one by one. First, pooling layer extend the full depth of the input data. This is wrong. We know that the pooling layer will not change the depth of any input. Basically, just manipulate on the image size, the depth won't change. Secondly, pooling layer reduces the spatial dimension of the input data. Yes, that's the usage of the pooling layer. Reduce the spatial dimension, that is the size of the output. Then pooling layer are used to pick up large scale detail than just edges and curves. Yes, usually after convolutional layer, the features extracted are only some edges and curves. But the pooling layer, by using some pooling filters like max pooling or average pooling, can just pick up some larger scale details. This one is somehow confusing. Pooling layer does not use activation function. Yes, the first half is correct. It does not use activation function. The second is wrong. They are not linear layers. Pooling layers are not linear layers. If you think about what is the max is that consider subregion, you take some maximum value, or the average, you consider some subregion and then take the average. Actually, those operations are not linear, right? It's not linear. They operate on these subregions and get some non-linear filters to do such pooling. So the second half is not correct. Pooling layer, they are not linear layers. And the last one is correct. Pooling layer help to decrease computational complexity because after pooling layer, the output size will get reduced. So basically, it reduces memory usage, reduce the computational complexity. In the meantime, pooling layer can also use to avoid overfitting. So the last is correct. So the correct options about pooling layers are these three statements. All right, so that's all for today's quiz. So any questions regarding the questions? Okay, perfect. Then see you in next class. Next class, we will start a new topic. That's the minimax and alpha beta pruning. So see you on this Thursday.